So in a previous video on this channel, we looked at the finite well. Basically a quantum well, you put a particle in there and you ask what energies can that particle take when it's inside the well. What we found is that for bound energies, where the energy is less than 0, there's certain states that it can take. And depending on the depth of the well, there'll be more states that it can possibly take. Now in this video, we're going to expand on the finite quantum well. We're going to look at a sequence of such wells, spaced apart from each other. And you might ask, well, why are we doing that? Well, it turns out that this sort of structure is a really good representation of crystals and solids. In addition, the technique we'll look at for solving this system is often used by quantum chemists to get the allowed energies of an electron in these sort of complicated molecule structures. Be sure to like and subscribe, join the Discord server, and enjoy. So for packages today, we got NumPy and Matplotlib. We're going to be doing some stuff with matrices. So this is solving for the eigenvectors and eigenvalues of a tri-diagonal matrix. We did this actually in the last video on the finite square well. And then a little bit of interpolation of functions because we'll need to solve integrals. And it turns out that having an interpolation will come in handy. Quad for solving integrals, and I don't need this. This should not be there. So let's think about the theory of what's going on here. We have an electron, a single particle, but in a sequence of wells. So there's not just one well anymore. There's sort of well, 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 well. And you say, well, what are the allowed energies? If I put an electron into this sequence of wells, what energies can I get? And so just for a plot here, I just sort of make a sequence of wells. And so this might be the potential energy as a function in space. Maybe this is like a Gaussian well. And you can see that here, there's sort of a well here, a well here, a well here. If it was just like a single well, which is the single case of the finite square well, this is a curved well, it would just be a well sort of in the center here. So this is sort of representative of like a crystal because there's sort of protons in a crystal and those form wells for the electron. So if you put an electron into a crystal structure, you use this sort of theory, what we're going to get into shortly, to solve for the energies of, what are the allowed energies of electrons in crystals. And that's important. And so what you really want to consider is the bound energies of the electron. Because of course in the finite square well, you can have unbound energies where the energy is greater than 0, so it can escape the well. But what we're really interested in here is the energy less than 0. So what are the allowed quantized energies less than 0, so the electron is stuck in the solid. So of course you could just go and take this potential and solve the Schrödinger equation numerically like I did in my other video. But the problem, of course, is when you're solving this in 3 dimensions or 2 dimensions or whatever, and you have many of these, it becomes difficult to solve the Schrödinger equation exactly. And so you build up these approximation methods that work really well to get energies. This is commonly used in quantum chemistry to get the energies of sort of molecules with multiple protons. It works for crystals as well. It's known as the linear combination of atomic orbitals. It's LCAO, approximation. It's a approximation method used to find the quantized energies in a crystal. And we'll go slowly through the notation that we're going to use. It's important that we specify the notation carefully. So the big thing about this model, this is the huge assumption that we make, is that the molecular states, so you have your state, your wave function of the electron. And of course that can be arbitrary, right? You can have any sort of wave function you want, but the model assumes that the only molecular states that you can take are a linear combination of the states for each one of the wells. So for example, you have a well here, a well here, a well here. You have a ground state here, a ground state here, a ground state here. These are just functions in space in one dimension. And it says that you can only have linear combinations of these are what the states that your system can take. That's not true in general, but it works well for finding the energies in our case. So for example, if you have like 3 ground states and 3 consecutive wells, it says you can only add those functions together, so you can get multiple sort of bumps. And you get more states as you get deeper wells and more bound energies. Remember, the deeper the well, the more bound energy states you have. That's in my previous video. Then you sort of get linear combinations of, each of those in each of the, say, 3 wells. So the notation we'll use, the bracket notation. And this is very important to get this early on. I was sort of working on this video and I kept messing up the notation. So I want to be very clear about what this represents. I represents the ith energy of a well, right? So 0 would be the ground state, 1 would be the second excited, third, fourth, whatever. And so the energy is inside the brackets here, right? The energy is what you put inside this vector. And then the subscript j, that's the well that you're in. So for example, 0, 0, 0 inside, and then 0 subscript would be the ground state of like the central well, for example. And then you go 1 over, and you have the ground state of the well next to it. Well, in that case, I would still be 0 because you're considering a ground state, but you're the well next to it, so that would be j equals 1. So this is the well index of the state of the well, and then I, what's inside the bra there, that's always the energy. So this represents the ith excited state of the jth well. So if I look up here, I would have a ground state here, a ground state here, a ground state here. So 0, 0 would be this sort of ground state here. And then 1 inside the bra, subscript 0, would be like the second excited state inside here. And then if I'm considering the ground state of the well sort of over here, that might be 0 inside the bra, subscript 1. So just get that notation down. That's what this means. And then you add these up together. This is what the LCAO approximation says. It says that any state is represented of the sum of all these combinations. So you can add states of the wells themselves and then also adjacent wells. And you're sort of adding all these wave functions together to get a general wave function. In the LCAO approximation, then, these vectors form a complete basis, right? So that's important. And so as an example, suppose we have 3 wells, each with 2 states. So there's a certain depth to each well. They have a ground state and a second excited state. These are the bound energy less than 0 states. So in vector notation, we could write any state of our system. This is the approximation, right? It's an approximation. But in this approximation, we can write our state like this. A vector has 6 components. These represent the ground and first excited state of the 0th well, the ground and first excited state of the second, and the ground and first excited state of the 3rd well, sort of like this. And so we can represent our quantum vector, our state, like this, and it tells you how much of each wave function contributes, of course, to your state. So for example, if this was just like 1, 0, 0, 0, 0, 0, 0, it would just be sort of the ground state of this well. And so we can write, like I said, any vector looks like this. It's C1 times 0, 0. This is the ground state of the middle well, the excited state of the middle well, then the ground state of, maybe this is the left well, the excited state of the left well, the ground state of the right well, and the excited state of the right well. So any wave function can be expressed like this. Now the question is, what's the Hamiltonian of the full system? As soon as we get the matrix, by the way, because our state is represented as 6 things here, our Hamiltonian in this particular example with 3 wells, 2 states, is going to be a 6 by 6 matrix. Once we have that matrix, we find the eigenvalues and eigenvectors, and we know everything about our system. We know all the bound energies that our system can take in this particular well system. So the question is, how do we actually get the Hamiltonian? Well, the Hamiltonian is H is the kinetic energy, T, P squared over 2m, plus the sum of all the potentials of all the wells. So you have the first well, the second well, the third well. This is going to be a function of position, the full well system. So each element of the Hamiltonian matrix, this is just a fact, when you have a certain basis. In this particular basis, this basis here that we're looking at, each component of the Hamiltonian looks like this. And we have 6 basis vectors here, and then these would be like the 6. I would go from like 0 and 1, but then you also have 0, 1, 2, so you have 6 basis vectors, and each component of the Hamiltonian is just basis vector, basis vector. That's by definition what the coordinates of a matrix are. So again, once we have this matrix, we solve for the eigenvalues, eigenvectors, and we're done. And that's sort of what we're going to do in this video. But we need a way to get to these elements. Like I've said that these are the elements, but the question is, how do we actually extract these given this information? This is the sort of trick to this method. And so what you do, and this is a super clever trick I saw in, I think it was McIntyre, Quantum Mechanics. You can express your Hamiltonian in a really clever way in order to get these values. So you write the Hamiltonian H like this. H is Hj, this is something that I'll define, and then V hat J. So the question is, what are these? Well, Hj, remember J is the index of the well that you're in. The middle well, right, left well. That's J tells you about what well you're in. Well, Hj is T plus Vj is the Hamiltonian only corresponding to the jth well, right? That's just a way you can express it. So I give you J and I get a new Hamiltonian that depends, it's just for each well. So everything is 0 except for that sort of well there in terms of potential. And V hat J, right? So I have Vj here. V hat J is the sum of all the other wells except for the jth well. So I have this new v hat j here. So it's all the sort of potential of all the wells except for the jth well that you're considering. And so what I'm going to do is I'm going to define something n is j minus j prime. So j prime is just an index of some other well, and n is the number of wells between the jth well, which is the one you're considering, and some arbitrary well. That's like the spacing of wells, the number of wells apart. And then you can express the matrix elements like this, which I have up here. So I just plug in h as hj plus v hat j, just right in the center here. Now hj times ij, the question is, what is that? Well, hj is the Hamiltonian of the jth well, and ij, this vector here, is the ith energy of the j well. So this is just the eigenvalue equation. Hj ij is ei times ij. It extracts the ith energy. Remember, I represents the ith energy, so I get the ith energy here, ij. And now inside this, you don't have operators anymore. You just have a scalar value, an energy, and this function here. And you can write this as an integral, right? Remember, you put like x here, and you integrate from negative infinity to infinity. That's like the definition of the, I forget, the dot product, I guess, of the bracket notation. And I just expand it. So my I prime j prime, right? That's phi I prime star. That's just by definition of this. X plus or minus nb. So I have j prime here. And this phi, this wave function is going to move over. And by the way, think about this a little bit, because this is where it gets a little complicated in the video here. But this function here, j prime, is going to be n wells away. So I have a wave function that's separated from my jth well by a spacing of n times b. And it should just be a minus here. Doesn't really matter. But, you know, it just says that the spacing between these two wave functions are nb apart. N times b is the spacing between the wells. So n times the spacing of the wells, and I get my wave function that's sort of moved over here. This is just the function that's right in the center, ei plus v hat x. And then my wave function phi I of x, because this is I. And you'll note that there's no j's in this equation. And what's really happening is you have a wave function that's basically centered at the origin, and then this other wave function here that's shifted away from it. And that's sort of exactly what you have I prime, j prime, and ij. It's because these wave functions are separated multiple wells apart. And so think about this carefully, go through it slowly. It should make sense. There's nothing mystical or magical here. It's all pretty straightforward. And basically, if we solve this integral for every element of the Hamiltonian, we can get the Hamiltonian matrix. So if it's 3 wells and then 2 states per well, I can find 36 different integrals, 6 by 6 matrix. It's pretty simple to do, and you can solve for the Hamiltonian. So the question is, what do you need to solve this integral? All you need is your energies of your single well, EI, your potential energy, which is the periodic potential, but you know the potential because you solved for the single well. So this all has to do with a single well. This has to do with a single well. This you can obtain if you know the potential from that single well. And these are the energy eigenvalues of the single well. So everything of this multi-well system, all the components of the Hamiltonian matrix, are written in terms of things that you obtain from the single well. And of course, we solved for that in our previous video. So with all the information just from the single well, the eigenvalues and the eigenstates, we can find everything we need to know about this multi-well system. And that's the beautiful thing about the LCAO approximation, is that all the components to solve for things, you only have to solve for a single well. You put the pieces together and you get the energies for the multi-well system. So this here, this function, is a summary of everything I did in the previous video. It takes in x, which is your position, right? It's just an array of values. V is a function of potential energy and some scaling factor V naught, and it returns the energy eigenvalues and eigenstates. And now I'm not going to go over this code a lot, but it's contained in my previous video on the finite square well. I'll put a link above so you can see. But watch that video, and all this information here, it's very short, is basically a summary of everything that I did in this video here in the numerical part to solve for the finite square or finite any well. And so I give it my position, my potential, and some scaling factor of the potential, and it gives me my energy eigenvalues and energy eigenstates, which I then plug into this function here, and then I can get my Hamiltonian for the multi-well system and get the eigenvalues and eigenstates of that system. So I'm going to consider a few examples in this case. The first thing we're going to do is we're going to look at the finite square well. I have V naught is 1 electron volt. That's a potential. The well width is going to be 0.35 nanometers, and the spacing is going to be 3 times the width of the well. So 2A, remember the way I defined the well in this older video was it goes from negative A to A, so the width of the well is 2A. Then we'll consider a slightly deeper finite well. This will have 2 bound states rather than just 1 bound state. Remember, the deeper the well, the more bound states you get. And then we'll also look at a Gaussian well. So the point of this is that this is a numerical method where you don't have to consider these sort of absolute cookie cutter versions of wells. You can look at arbitrary functions as well. So we'll look at this particular system here. So let's first get the parameters for this first well here. I'm going to set V naught, that's my scaling of my finite well, that's 1 electron volt. I'll define H bar, the mass of the electron, the spacing of the well in terms of meters, and then F. And F is a factor, by the way, that allows me to go from dimensionless parameters to dimension-full parameters. So what I do is my V naught, remember in my older video, I defined V naught prime as V naught over H bar squared over 2ma squared. This is a dimensionless potential. And so F is H bar squared over 2ma squared. And when I find the energies, in the end, I'll get my dimensionless energies E prime. I'll multiply by F to get E. Again, if you haven't seen it, watch the older video. That should be like a prerequisite to this video. So F is H bar squared over 2ma squared. And then I define my dimensionless V naught, and B is dimensionless, just equal to 6, because the well width is equal to 2. It goes from -1 to 1. Well width is 2 in terms of my dimensionless distance. So these are just some numbers. I'm going to set my example equal to 1. And for X, I'm going to go from -15 to 15. I choose a very large range to solve. The well goes from -1 to 1, but I'm solving from -15 to 15 to make sure I sort of approximate infinite boundary conditions. And my potential looks like this. It's minus V naught well. And I go over sort of what this corresponds to in my previous video. But the point is that I'm considering the first example of my 3 examples. I define the potential this way, and I can plot this potential because I have X that goes from -15 to 15 with 100,000 points. And this is basically what my potential looks like. This is a single well potential that I'm solving here. Then I get my energy eigenvalues and energy eigenstates for this single well. And again, that's the whole focus of the other video. I wrote a function, solve single well, to do this in this video, and I can look at the energies. So remember that these are dimensionless energies that I'm looking at right now. If I want the dimension-full energies, as specified in this video, I need to take my dimensionless energies and multiply by H bar squared over 2ma squared. That will give me my energies in like units of this video in terms of electron volts, since this is how I specify V naught. And so I look at F times E. There's a single bound state for this well because it's not very deep compared to its width. And I have minus 0.405 electron volts. I can also plot the wave functions. So the way that I'm plotting it here is I loop through all the wave functions and plot them. In this case, there's only one wave function. So I plot it and it looks like this. So it's basically just bound sort of inside the well like this. So it's contained, the well is right here, and the wave function says that the electron is sort of contained in this area. But of course, there's a probability that it escapes the well, and that's what happens in quantum mechanics. You could have less energy than the height of the well, and there's a probability that you'll be found outside of the well. So this integral here that gives the components of the Hamiltonian matrix, I need to integrate these wave functions, but right now I have them in a numerical format. I just have points and I have X values. And so what I'm going to do is I'm going to interpolate and get it so that I have a function where I can plug in any value of X, and then I can take the integral of this a little bit simpler. So again, in my size array, my array of multiple wave functions, I have only one wave function right now. But what I can do is, for example, if I interpolate my wave function. So I'm going to take my first value of size, 0, and I'm going to call this func. This gives me a function where I interpolate x, which is of course the domain, size 0, which is the range, the blue height here. I don't want it to give bounds errors. I want it so that if I'm outside this range here or outside this range, it returns 0 and it returns 0. So it's not going to return an error if I give a value outside where it interpolated. and the fill values are going to be 0 and 0. That's just going to help when evaluating the integral. So here I loop through all my values of psi, because of course in some cases I'll have more than one bound energy. I do this for psi and size, and I get a list of functions, right? So if I look at size f, in this case I'll only have an array of one value. So it's this thing here. And I can take sort of the 0th element, and that gives me my ground state energy. And I can plug in a value here, or my ground state wave function, and I can plug in, say, you know, what is it equal to at outside the well here? At 2, right? So 0, 1, 2, and it will give me this value here. And if I'm outside, if I give it a value of 16, it should return 0, which is what I've set it to do automatically. So now for the slightly tricky part, and this is a really beautiful thing I found searching online for defining v hat of x. Remember that v hat, so for example, if I'm looking at the jth well, so right here, v hat j of x has all of these equal to whatever, except for the well you're considering equal to 0. And in our case, v hat, it's the center well here. So it's all these, and then this is equal to 0. So the question is, how do I, if I'm given my potential of a single well, how do I define a periodic function like this? And there's a beautiful way to do this in Python. If I have like 15 or 16.2 modulus 2, it gives me the remainder. So the remainder, when I divide 16.2 by 2, it's sort of weird, a remainder with decimals, but the remainder of 0.2. Same thing if I go like 0.23, whatever, this, the remainder will be like basically this value. So here I'm plotting v of x, and you can see that, of course, it goes from -1 to 1, as the well does. And suppose I want to repeat it every 5 units. Well, then I can go v of x modulus 5. Because as soon as x gets to 5, it's going to go back to 0. And then it gets to 10, it goes back to 0. And then it gets to 15, it goes back to 0. And I can plot this, and I get something that looks kind of like this. But you see that it's off-centered a little bit, because negative values, when it's less than 0, unfortunately, if x is like -0.1, there's an issue here. So the question is, how do you get around that? Well, for that, I would go x minus 2.5 modulus 5. That removes this like sort of negative behavior here. But the problem is that the whole well is shifted over now. In order to shift it back, I have to add that spacing that I want. So I subtract 2.5 again. And then I get the periodic behavior of my well like this. And that's sort of the mystery of what's going on here. So play around with that and see what that is. And to get rid of the center well, then I just subtract the potential in the center as well. So then I get my v hat of x. So the potential of all the wells except for the one centered at x equals 0. And again, as a reminder, the reason why we want that is because of the trick, where you separate the Hamiltonian into the Hamiltonian of the well j plus this potential from all the other wells. So here I have v prime of x. And let's actually look at what's going on here. Let's sort of summarize sort of the distance that we've come so far. And this should not be a v prime of x, this should be a hat. And so let's plot everything we have so far. So for example, here's v hat of x from negative, let's actually go a little bit farther. Let's go -20 to 20. So here, this red line here is v hat of x. So it's the potential of all this periodic well system except for the one at x equals 0. And here I'm plotting the ground state of the middle well and the ground state of this well here. And of course, the LCAO says that we can only take linear combinations of these two functions, and that any state that our system takes is going to be linear combinations of these functions. And now we need to evaluate this integral. So psi I star, by the way, these are real functions, so it doesn't really matter here. The complex conjugate is whatever. But you could think of like psi I as being like this blue function here. Then I have ei, which is just a number, plus v hat of x. This is this red function here. And then psi I star of x plus or minus nb. Well, in this case, n is equal to 1. It's shifted over by 1. And the well spacing is 6, I believe, here. So I have spacing of 6. So b is equal to 6 in dimensionless quantities. And I have all these functions here, so it's very easy to just integrate them and get the values that we want for every element of the Hamiltonian. So this is a function here that does that. It takes my list of functions, eigenfunctions. It takes my energies, eigenenergies. By the way, these are going to be interpolated functions. They take in any value of x, right? And it returns whatever psi is there. So it sort of interpolates this blue array of values. Same thing with the yellow one. And then I also want psi I of x plus or minus nb. Well, I have this interpolated function here. All I have to do is feed it a shifted value. So I define this function here. Quad is just the integral, and it's the integral of this function lambda x, while I have my size function, the first index, so that's like I1 here. Instead of I and I prime, I use I1 and I2. So here's I1 of x, that's this function, times this function here, size of I2, so this is like I prime, the I2, x, and I use minus NB. It doesn't matter, it's going to give the same result either way. And then I also multiply by my energies corresponding to I, plus this v prime function that I defined up here above, of x, the well spacing, and then of course the potential scaling. And I'm going to integrate from negative 20 to 20 to make sure I sort of get everything that I need. So of course this thing here, it's going to be an element of the Hamiltonian matrix. It's going to have units, well, it's going to be dimensionless, but when I multiply by the correction factor f, which is h bar squared over 2ma squared, it will return me an energy value. So for example, here I compute the integral and I multiply by the correction factor, and I would get something that has, in units of electron volts, minus, it's about 97 milli electron volts. So now we need to find the Hamiltonian matrix. And the most difficult part here has to do with indexing, right? Because you'll note that I have my Hamiltonian values as like I prime, j prime, h, I, j. So there's sort of two indices here, I and j, but I really want like 0, 1, 2, 3, 4, 5 as my Hamiltonian values. So the tricky part that you really have to wrap your head around is that there's like 0, 1 for the energies and 0, 1, 2 in the 6x6 case. But really, I want indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5 for my Hamiltonian matrix. So we need to make sure we do that carefully. So let's consider a case where I have 20 wells. And there's going to be multiple states per well. In our case, we only have one ground state per well. And so that's going to be the length of my E's, right? So I have my number of wells and my number of states per well, right? So E's is just an array of one value. So n states will be 1. And I'm going to create a Hamiltonian. And the Hamiltonian is going to be the number of states per well times the total number of wells. Of course, in the 6x6 case that I was talking about above, I would have 3 wells, 2 states per well. There's going to be 6x6 Hamiltonian. So it's just the number of wells times the number of states, and that gives me my Hamiltonian. And so I'm just setting everything equal to 0, and we're going to sort of go step by step and fill in all these values. So the little trick that I do from going from like, of course, in this case, up here, again, this is the most complicated part of the video. From going from like zeros and ones and 0, 1, 2s to go from 0, 1, 2, 3, 4, 5 for the indices of the Hamiltonian, I do a little clever trick here. So I have all my eigenstates and I'm going to list them in this order, sort of like this. Of course, in my case, I only have one energy eigenstate per well, the one ground state, and then 20 different wells. And so what I'm going to do is I'm going to list them like this. Right now I have my size interpolated functions as a list like this. And I'm going to multiply this by the number of wells, n wells times this. And now I get a list of all these functions. Now, if this had 2 states per well, it would be like ground state, excited state of first well, ground state, excited state of second well, ground state, excited state of third well. And you'll see that in future examples. But this is sort of a clever trick to handle things. Same thing with my energies. I take my number of wells and I multiply it by the list of my energies here. And so again, here I only have one energy, so it gets repeated over and over and over again. But in the case of ground state and excited state, I would sort of have ground state, excited state, ground state, excited state of each sort of well. And so again, you'll see that in a later example. And then what I do is I sort of loop through, and again, I'm using a for loop here. I say not to do that in Python, but it's not the limiting factor in terms of computation here. It's solving this integral, which really takes time. So the loop isn't a big deal. And so what happens is I do this trick where I only fill the upper triangle of the matrix. But what happens is then I add the transpose of the matrix to get both the top and the bottom filled properly because it's a symmetric matrix. But what happens is that doubles the main diagonal. So then I refill the main diagonal. If you're wondering what's happening there, that's essentially what I'm doing. And so I go from I'm basically looping through the matrix, the upper triangular portion. I get my well 1 and my well 2 index. These are important because this gives the spacing between the two wells. And so, for example, it's not super clear with the case of one well, so I'll come back to this when I go to my next example. And then I fill my Hamiltonian with my 2 indices. This is just the location of the This is the location of the point in the Hamiltonian. I compute the integral that I defined, and I pass in my total list of size. So it goes through each of the size, the ground state, excited state, next state of the first well, second well, third well, fourth well. So I have n states per well, n wells, and that gives me my size tot array, all my eigenfunctions. Same with my energies. I give the indices. These values will be used to index my eigenstates and eigenenergies. Of course, I give the same spacing, scale of the potential, and then my spacing between the well, which I'll get to when I get to the next example. And so I fill the off diagonals. I'll just make sure to run this again. It runs fairly quickly for the size of this problem here. And then, of course, the main diagonal gets filled twice when I sort of add the transpose of the matrix to the matrix. So I fill in the upper diagonal, then copy it over to the smaller diagonal. So I refill the main diagonal. And I can show a visual representation of the Hamiltonian here. So this is what my Hamiltonian matrix looks like. And so I sort of have these large values here, and then it sort of decays as you go to the sides. And it's essentially basically a tridiagonal matrix. We can solve for the allowed eigenenergies and eigenstates. So that's what I do here. I solve for them, and let's actually plot the allowed energies of this system. And you'll see that this is very interesting. So this is just a plot like this. Basically just ignore the x-axis, but this gives me all the different energies that I can take. Of course, I'm plotting F times them, so I'm going into units of electron volts. So it says that my allowed energies sort of form this spectrum here, like this. And as you'll see, if I add more wells to the system, and I sort of rerun this, it'll take a little bit. My matrix, I can show the matrix is just going to be larger because I have one ground state per well, but then now, of course, I have more wells. So it's going to take a little bit of time to fill this. Now, of course, my Hamiltonian is bigger because I'm considering more states because I have more wells. Larger Hamiltonian here. And now I look at my energy eigenvalues and vectors again, and you'll see that this just becomes more dense. I have more states here. And it turns out as the limit of the wells goes to infinity, I have a continuous energy spectrum, and that's exactly what I wanted to get at in this video. For a crystal lattice of wells sort of spaced apart from each other, if you put an electron in there, the energies are no longer quantized. You actually have a continuous energy band. And if you study solids, crystals, scintillators, things like that, they talk about energy bands as electrons change from different energy gaps. They can actually change from like different bands. So you'll see that if I have not only ground states but excited states, I have one band and then I might have another band in another location. So let's consider the second example. And in this case, I have a 5 electron volt depth well. And so now I'll have more energy eigenstates, bound states in my well. So here I'm going to make sure I'm in example 2. It's still going to have this same potential. It's just slightly deeper. Now it's my dimensionless potential here. So this is if I have 5 electron volts, then my dimensionless value is going to be around -4. My h bar squared over 2m is approximately equal to 1. I can solve for the energy eigenvalues and eigenstates of this well. But of course, now I have 2 bound states. And let's plot the wave functions of this single well. I have a ground state and an excited state. So things get a little bit more complicated because now I have maybe many wells, but I have 2 possible states per well. So I do everything basically the same as before. And of course, now I can plot sort of ground states in these locations, but then maybe there's also going to be, it's not that many states. It's definitely not that many states. There's maybe one excited state. So for example, here's the probability density function of this state. And then maybe the probability density function of the eigenstate corresponding to this well here. So of course, I still have this function that computes integral values. And now we fill the Hamiltonian matrix again. So let's go back to 20 wells. And you'll see that now the number of states per well is 2. So I have 20 wells, and there's 2 possible states per well. So my Hamiltonian is going to be 40 by 40, because I'm going to have the first well, 2 possible states, second well, 2 possible states, etc., etc., etc. So this is where things get a little bit interesting, because now, of course, if I look at my size f, these are my interpolation functions. It sort of looks like this. I have this would be my ground state, and this would be my excited state. And these are sort of repeated over and over. My Hamiltonian is 40 by 40, right? But it's always ground state, excited state of first well, then ground state, excited state of the second well, if I'm sort of going across the row. And so in order to get all my basis vectors lined up, what I do is I take the number of wells and I basically just copy these over and over and over again. So if I go n wells times this, again, like I said, it's the ground state and then the excited state and then the ground state and then the excited state. And this basically, in order of this list, these are all my basis vectors. They're interpolation functions, but you could really think of them as basis vectors. This is sort of the first basis vector, the second basis vector, third, fourth, fifth. And I do the same thing with my energies. List of E's. And now I have the energies corresponding to each one of those basis vectors listed properly so that I can construct the Hamiltonian. And if I want the well index, well, that's where it gets a little bit complicated because, if I define, let's look at my energies, for example, here. And let's look at E's totes. So, for example, if I'm at an index here of maybe like, what is this? 0, 1, 2, 3, 4, 5, 6, 7. So here's index 7. And you might ask, well, what well are you in? I'm not in the 7th, or, well, in this case, the 8th. It's the 8th element of the array. I'm not in the 8th well. I'm in the 4th well, right? If I'm sort of down here, this energy corresponds to the energy of the 4th well in the sequence, but my index is 8. So the question is, how do I get what well I'm in? Well, I take my index, suppose I'm at 8, and if I divide by the number of states, it says I'm in the 4th well. So this is how it works. My index 0 is in the 0th well. My index 1, it's also in the 0th well. Index 2 of the full array there is in my 1st well. Also in the 1st well. In the 2nd well. Also in the 2nd well. And I go down that list and that will give me my well index. And that's how I get the spacing between the wells here, is based on my well indices. So that's that trick there for finding the basis vectors in order. So I do the same thing. I can fill my off diagonals and my main diagonal of my matrix, and then let's actually look at what the Hamiltonian looks like. And so now my Hamiltonian looks a little interesting. And so this is sort of the energy of the ground state of the 1st well, excited state of the 1st well, and you can see sort of the pattern is a little more complicated here for the Hamiltonian, which means we get more interesting behavior when we look at the eigenenergies and eigenvalues. So let's solve for the eigenenergies and eigenvalues of this matrix, and let's look at the allowed energies. And you see that we get this band structure, and it's exactly like I said. We have this higher energy band here that the electron can exist in. And we also have this lower energy band, and this is actually, it looks like one line. It's a number of lines here that form this lower band. And so as you get more and more states, as the wells get deeper and you get more possible like ground state, first excited, second excited, third excited states, you get more and more bands in your crystal. And this is shown in experimental practice. If you look at a scintillator, for example, they have different energy bands to them. And so what we've done is we've used the LCAO approximation to show that we get these sort of energy band structures when an electron is put in a sequence of wells. And so it's interesting. It's sort of quantum behavior, because it can't take any energy you want, but it can exist in these sort of quantized bands where you do have a continuous energy spectrum for a very large solid. Now, here's example 3 for the Gaussian well as well. I'll just go through this really fast. My well now looks like this. I get slightly different looking eigenfunctions, and if I look at my number of states, I have 2 possible states. And then, of course, my sequence of wells looks like this, my ground state, and then here's my my first excited state in this well here. I can compute my integral over and over. And let's look at the Hamiltonian. So you get another sort of interesting looking pattern here for the Hamiltonian. I can look for my allowed energies of this system. And you see that, again, I get this sort of band structure here. This is for a slightly different shape of well. So I have my energies up here, and then of course this would be a very much smaller band corresponding to the deeper states of the well. And you see that the energies corresponding to the lower band, they range very little. They sort of go from minus 21.4 electron volts to minus 21.379. Actually, I think these are dimensionless energies. So it's a small range compared to the magnitude, whereas the lower ones, of course, they cover a much larger range. Anyways, I hope you enjoyed this video on the sequence of finite square wells. If you enjoyed it, be sure to like and subscribe. Join the Discord server as well. There's a link in the description, and I'll see you next time.